So today, it's supposed to be a lab day, but I am going to use some time to finish the topic that I was doing yesterday, the day before rather. All right, folks. So on Monday, we covered the topic of regularization. I will quickly review that topic. And today, what we will do is I'd like to finish one more topic, which is backpropagation. Backpropagation is a straightforward topic. I don't want to leave it for next week because we have other important things coming up, convolutional neural nets and other things coming up next week. So I'd like to finish it off right today itself. I'll also briefly touch upon optimizers and we'll handle the rest in-depth discussion on optimizers in one of the extra sessions. So, and this is all so that we can get started with convolutional neural networks next week. So let us recap what we uh, learned on Monday. So if you're looking at my screen, you will notice that we basically said that regularization is a method to decrease overfitting to data. If you take an overtly complex model, you run the risk, if your model has too many parameters, you run the risk of overfitting. And the way you avoid overfitting is by regularization. It dampens the oscillations, basically. Right? And this is the basic idea that you want to get a curve like this pink curve, which is complex. But you don't want to get the yellow curve because the yellow curve is complex, but it has overfit the training data, and so is likely to do very poorly on the test data. The reason it does poorly is because it has fit not just to the information content of the training data, it has also learned from the noise. It has fit to the noise, and that is a bad thing. Right? And the trade-offs are that you can take a very simple model, like for example, this blue model, which will have high bias errors. Then you don't have much that you can do about it. Or what you can do is take a bit more complex model, but you can regularize it. When we talk about regularization, we talk of many techniques of regularization. In particular, we talk about 7 ways to regularize. One is simply taking the batch size in deep neural networks. When we set the batch size, don't make your batch size very big. Make it small so that your loss surface does have perturbations. It keeps wobbling around, and you that makes sure that you don't get caught up in local minimas, right? The suboptimal minimas. The other way that you can deal with it is by using simple data augmentation techniques. We talked about a picture. You have a picture of the cat, invert it upside down, it left, right, in lateral invert, take sections of the cat, right? So that it is still a cat, and do all sorts of things like that. And you therefore have data augmentation. Now, the rule is when you have complex algorithms, one easy way to tame them, to tame the oscillations, the overfitting, is just to give it an overwhelming amount of data so that those oscillations get dampened and you have a good model. Now, that is data augmentation. The other is to ensemble it. We are aware that, for example, in ML400, we learned that when you have a random forest is an ensemble, is a bagging of lots of trees, weak learners. When you ensemble a lot of individual weak learners, you get a pretty good learner. Right? So that's where we have a theorem that says that if each of the weak learners is able to make better than 50% prediction, just a little bit better than 50% prediction in binary classification, the overall ensemble will make impressively good predictions. Right? So that is using ensembles. Now remember that sometimes it is said that a neural network is itself an ensemble of nodes. Now that's not enough. You can take an ensemble of neural networks and do that. So you can take, you can train your neural networks with different properties. You can train it with different input features, things like that. And, and then you can stack all those neural networks together and get a better prediction. And that will regularize it. Another thing you could do is simply batch normalization. The rule with neural networks is, and we talked about it, that in the activation function, if your response from a neural net is any one node is too high, then it becomes the input to the next layer, which is big, and that input causes a saturation of the activation. Activation will become close to, let's say, if you are doing sigmoid, it will just asymptote to one or minus or zero. So the learning happens very slowly. Uh, and so one easy way that you can control all this is by a batch normalization. Um, it's a good thing to do batch normalization, do that. Then the early stopping, like you know that in the beginning, the neural network will be fitting to the data. Then towards the end, it will start fitting to the noise. So you should know when to stop. The way to do that is after each epoch, you see the divergence between training data and test data, the performance on training and test data. If the if you see that test data is beginning to become significantly worse than training data evaluation, performance on training data, you know it's time to stop. That is one. And then comes this the next method, which was dropout. What you do at each layer, it's sort of like a Cheshire cat. You make these nodes disappear for a batch. So as one batch of data, so one step, one iteration goes through the data, through this network. Certain nodes are just passivated; they just go dark. They preserve their old weight values. You don't remove them, but they don't learn. They don't do forward passes or anything. They just completely go dark. And then um, what it leads to, once again, is it is a form of introducing um, blurring the optics on the loss landscape. It's sort of introducing a bit of noise into it. And what it does is it makes sure that it's unstable. The loss landscape remains unstable, and you don't get trapped in very shallow local minimas. Right? That's a virtue of this dropout. And lastly, we talk about the more complicated L1, L2 regularization. These regularizations, of course, by the way, I've mentioned that L1 is lasso and L2 is ridge. You will also see a new term often used. Let me just write it here. L1 is lasso. People refer to it as lasso. They also refer to it as a Laplacian regularization or Laplace regularization. Why is that? It has to do with the Bayesians. Uh, and we haven't done Bayesian thinking, but one of the beautiful results, if you make an initial hypothesis, a prior hypothesis of the weights, and the shape of the prior is a Laplace function. Laplace functions are usually peak functions like this. And we won't go into it because it's a bit more complicated topic at this moment. If you start with a Laplacian prior, it turns out that L1 regularization automatically comes out. And in the same Bayesian technique, if you start with a Gaussian prior, a bell curve, a Gaussian, L2 is also called a Gaussian regularization. Because if you make your initial guesses of weights as distributions, as Gaussian distributions, then L2 regularization automatically follows from that. Now, I've used some esoteric words. If it doesn't mean anything to you, don't worry about it at all. It will make sense only to people who have done some amount of Bayesian learning with me. But just to know that these are other words that people use for L2. Gaussian is another, and ridge. L2, Gaussian and ridge are the same thing. L1, lasso and Laplace are the same thing. Gaussian, Laplacian. So that those are the methods of regularization. Now, we also talked of the fact that L1, L2 are actually the same method. The fundamental idea is that you constrain the weights. You say that you're not willing to let the weights blow up. So you set a budget and you create a unit circle around the origin in the parameter space for weights and biases. And you say that beyond a certain measure, they can't grow. If you constrain it to a certain size, then you can't then go and look at the absolute minima, because the absolute minima may happen far, far away from the origin. But the best you can do is a point like this, a point that is a point like this, an optimal point. And this point is your constrained optima. Let me write it. Constrained optima. Right? This is the best you can do at this point. And there's a beautiful geometry to this. And just as a recap, at this point, it turns out that the perpendiculars, the gradients, they are obviously pointing in opposite directions. So they have to be multiples of each other. And when you take that and you write it out, it turns out that in a couple of steps, you can come up with a new loss function, which is made up of the sum squared error term and this other term, which is the regularization term. Now, in this regularization term, you notice that this guy, lambda is the hyperparameter. Usually people take values of lambda starting with 10 to the minus 4, 10 to the minus 3, 10 to the minus 2, 10 to the minus 1. So you take it in powers of 10. You can even go 10 to the minus 5 sometimes. Right? And you can use that and see which is the best value of lambda. So here is one intuition. I said that in the parameter space, in the parameter space, you make a unit circle that could be a diamond in the case of Manhattan norm, or Euclidean. It will really look vibe with a natural definition of a circle. Right? So you set a budget, and this is your budget. This is as far as you can go, radius. Right? One way to think about radius is your radius is inversely proportional to 1 over lambda. Right? So what does it mean? If you want to give a large budget, lambda should be small. If you want to give a small budget, lambda should be large, right? Because they are reciprocals of each other. So what it means is you make lambda very big, you are over dampening the system, right? You're pushing you're not giving much choice to the model. It has to find the optimal value within a very tight circle around the origin for the parameter space. You relax it a little bit and then you get more flexibility. And if you go and look at this picture, what it means is that, see, if you take a budget that is only this small, you realize that the optima that you will find will be not as optimal. The residual error, the error that remains, will be significantly more than if you have a slightly bigger budget. So one question that comes, therefore, is what is the optimal value? How do we determine the optimal value of lambda? Would one of you like to take a guess? How do you find the optimal value of lambda? Anyone would like to guess?
By trial and error.
And how would you do it by trial and error?
So one value, then find the test loss and compare it with another value test loss.
Excellent. Yes. So as you slide your lambda back and forth, what happens is that your training error will be something, but your test error, you have to look which of these gives you the least test error, and you have to go with that. Right? So therefore, it's a hyperparameter of the model that you have to somehow find the best value of. The traditional methods used to be the grid search or the randomized search. But as we are going to learn in this workshop series, today we have more smarter ways of figuring these out. We'll talk about automated machine learning. And one core topic there would be hyperparameter optimization. One of the hyperparameters that we will optimize in a smart way will be this the lambda parameter. The summary, that the basic thing to remember is a bigger lambda means a smaller budget, smaller circle that you're allowing. So you're only, the bigger the lambda, the smaller the value of weights that you're allowing, right? And in a way, you can see that from this equation. See, if you look at this equation, the loss comes from two parts. One is the error part, and one is the weight part. So what happens is, if you want to minimize this, you would like to keep your weights low, right? If you keep the weights low, I mean, if lambda is big and weights are very small so that the product is reasonable, what will happen is, if you make it too small, the weights too small, then you realize that the error surface will meet at a point that is too, that is too high sum squared loss. So as you move out from these contour surfaces for the error, the sum squared error, or the first term begins to go up, but the penalty term begins to go down, because the penalty term is this square of is basically the size of this particular circle. So the more you shrink the circle, one term in the loss decreases, but the other term increases. And the whole point is, where is the perfect balance between these two, right? At which you get a good test error, a minimum test error, right? So that's what it is. So any questions, guys, before I continue? This is regularization, and I have added into the quiz that I'm about to release tonight or tomorrow a lot of questions about regularization. Now, regularization is mentioned in your textbook, main textbook. Please do read that. It is also discussed, the L1 and L2 are discussed in the ISLR, the textbook for ML100 and 200, Introduction to Statistical Learning with R. So please go and review there. The review in ISLR is more detailed. It's more, it goes slowly and explains the concepts. The review of it in the textbook, the deep learning textbook, is a little bit quicker. It just gives you the summary of it. So if we are clear with that, I will then move on to the next topic. Should I, or are there any questions, guys, before I do that?
So as if the prediction here is also a function of the weights, correct? The
Yeah.
error term.
Yes, it is. So here are the steps you look at. See, when you do the model, you have a model, right? Model is made up of these weights, and like I'll just write weights, where bias is equal to W naught, right? These weight terms. So what happens is that for any given value of the weight, input vector goes out, y hat comes out, right? From y hat, right? What do? From y hat and feed in the actual y, you get the loss, y minus y hat. You get the loss function. And in the case of binary classification, or sorry, classifier, it is the cross entropy loss. And there are many loss functions, but the common ones we will stay with are the sum squared error and the cross entropy loss. So whatever the loss is. Now you ask this question, how do I minimize the loss? So the loss is made up of these two terms, right? And so what you have to do is, if you try to minimize the weight, how? And that is the process we will learn today. You sort of how do you, like, as I told you, you can imagine that this box is made up of all of these resistors which are going through some act distortion function. What you're basically saying is that these are rheostats. You now you can start sliding your weights back and forth. If you think of them as rheostats, you're just calibrating your rheostat, fudging around with it and seeing what happens if I change this weight this way and a little that weight that way, and how does it affect, therefore, the prediction and therefore affect the loss. And the thing is, we want the loss to decrease. Now, we learned a way to decrease the loss in a systematic way. Right? Uh, we don't want to fudge. We don't want to just guess um, an optimal value of W, the parameter values. The W star, in other words, cannot just be hard to just guess. And one can illustrate it with a simple example. Suppose you have data, and I ask you to find a best fit line. Now, how many lines can you draw on this plane? Can somebody guess? You can draw many lines, and each of them has associated with it a weight vector, which is made up of the intercept and the slope, B and W1, let us say, the bias or the W naught and the W1. Slope and intercept, each line has a separate slope and intercept. So one way you could do it is you could just randomly keep guessing the slope and the intercept, and then pick the one and keep track of the losses. And finally, you pick the one that takes this value. Now, why is that not a valid approach? Could somebody argue against it, please? What's wrong with that?
It's not feasible. I mean, most of the time you'll end up with the wrong estimate.
Yes. See, the thing is that in two dimensions, in two dimensions itself, there are infinitely many lines that you can start out with. Even if you limit yourself close to the origin, those weights, and you try to draw the lines, still there'll be lots and lots of lines that you'll have to play with. And it becomes a grid search. In higher dimension, it's a computationally very expensive grid search. That is one reason. Practically, it's not feasible. The second reason is, suppose you found amongst your grid search, you found a value that you think is the lowest amongst the ones you looked at. There is no proof that it is truly the best solution. Right? On the other hand, we learned about a technique which was gradient descent, if you remember. If you do gradient descent, then what happens? You take the shortest path to the minima, to the center. Right? I won't rehash gradient descent, but the idea is that every single shift of the weight decreases the loss. Right? So from step 1, step 2, generally, roughly, loss keeps decreasing. It might fluctuate a little bit, occasionally increase and so forth. And we saw that in our labs. Occasionally the loss again shoots up and then again comes down and so on and so forth. But broadly, the trend is that it keeps coming down, isn't it? And it comes down rapidly and in a systematic way. So that is why we value gradient descent as the optimization method. In this, I think one person once asked this question, but why do we not use second order methods? If you are into mathematics, one of the things that may come to you, those of you who have background in numerical computing, let's see, we are using gradient, which is the first derivative. And yet there are methods like Newton-Raphson and things like that, which utilize the second derivative, they use, and then so those methods can be used for smaller data sets. When your data sets are huge, it becomes a little infeasible. And those methods, again, we realize that in a world where we don't have a convex surface, globally convex loss surface, then the proven way, the one way that we know converges well, is the gradient descent way. It has been very well researched. It does extremely well. Right? And generally what happens is if you come from a background in optimization, linear optimization, and convex optimization, etc., you might be tempted to say, well, you know, there are other techniques that we can use. Why don't we go use that? But all those techniques have a place, but in this particular case, in the case of neural network, generally experience has shown that nothing beats some form of gradient descent. We all just use gradient descent in a practical way. It just works. And people have studied it deeply. You know what is going to happen. It's a known entity. Right? You know its behavior and so forth. So that's gradient descent. So any other questions, guys? So we will then move on to the next topic, which is a back propagation. Let's go to that topic. It's a very interesting topic. It seems to have been back propagation. It's at the heart of how a neural network learns. This is how neural network learns, right? So it is really at the heart of it. Now, if you look at the history of backpropagation, people thought it was discovered something around 1986. And then first people thought it was discovered around 1991. Then they realized that somebody had done work in 88, then 89 actually. Then they realized that work was done in 86. And now more and more historical, analysis shows that it is an idea that is powerful enough that many people discovered it independently, and the roots go back to 1960s and late 1950s. So practically when the computers came about, and remember those were the days of giant buildings. Computers used to occupy giant buildings and have big vacuum tubes and solenoids and so on and so forth, magnetic cores. Already this concept, this very interesting idea of backpropagation had been formulated in one way or the other. And I suppose it's a testament to how central it is to neural network that people have bothered to investigate the history of this idea and how far back it goes. So I'm going to explain backpropagation to you guys. Right? So the way I'll do that is it's today. Actually, I'll give quite a bit of the time to backpropagation. I do want to finish it before we go to the labs. Even though today is a lab day, because as I said, we won't get time later on. So backpropagation at its root needs one calculus concept before we understand what it is. And that calculus concept is called the chain rule. Now, most of you would remember what the chain rule is. It's a very abstract thing. So suppose you have y is some function of z, and z is some function g of, actually, let me write it the other way around in a systematic way. Z is some function of y, or w, and w is some function of y. Let me just go writing it, some function of y, and y is some function of q, no, let's not use q, f and g are gone. Let's say t of x. So you realize that if I change x, it will change y, that will change w, and that will change z. Do we see that, guys? A change goes like this, right? Is it making sense, guys? Right. So in other words, z is, if you write it, you can write it as a function of a function of x. This is just algebra. You take the value, what will Tx produce? It will produce Y. Now, what will G of Y produce? It will produce W. And what will F of W produce? It will produce Z. And so that is Z. So are we clear, guys? You see this relationship? Right? And you can represent it as a diagram if you so wish. You could say that X goes to the function, T takes it to Y, right? And then let us say that G takes it to W, and now I'll just deliberately make it into a triangle. This takes it to G of Y, T of X. And so this takes you to Z. And so there is some function, let me call that function composite function. Let that function be S, right? Which is a direct short circuit, right? So you can go this route, or if you know S, you could directly take the derivative of X. I mean, small changes of X will directly, you can plug it into this equation and you'll know how much change will happen or what the value would be for Z. So far, am I making sense, guys? I'm saying something quite simple, right? So just keep this picture in mind that you can write things in a very indirect way, right? So for example, an illustrative thing that people often say is that, suppose some major thing happens, cascading effects happen. Let's say that some company, well, I guess we are talking about weather and so forth. So what happens? Suppose we have a very hot summer in California. Well, high temperatures leads to the ocean getting warm. Maybe that leads to thunderstorms, dry thunderstorms. That leads to fires, and that leads to, I suppose, a lot of economic problems. Right? And we are seeing that, just taking a very practical example. So you can say that the amount of money that California has to spend is proportional to the number of fires in a given season. Number of fires depends upon all sorts of variables, but let us say that it has to do with weather conditions. Now, or in particular, number of, let's say, lightning bolts and whatnot. And the number of lightning bolts depends upon, or the number of storms depends upon, thunderstorms depend upon water temperature or land temperature. Maybe it's the land temperature. And therefore, a very hot temperature caused by weather can lead to indirectly to a lot of consequences. That's the concept of a function of a function of a function. Right? So a whole set of implications or consequences. This would change if something happened to X. That is the idea of this complicated rules. And now comes a very interesting thing. Suppose I ask you this. Suppose S is not, you don't know S, right? You know S only as f of g of t of x. I'm just writing this circular symbol because I don't want to keep making all those brackets. Right? So suppose this is it, z is this, but this is the best you can do with this, right? You want to write it like that, right? So now comes an interesting question. Suppose I do x changes by a small amount, it becomes delta x, right? How much does z change? So you want to know what is the change of z with respect to small changes of x. So what we want to know is how much does z change, a small change of z with respect to small changes in x. Right? So this is called, and there's a bit of calculus, but let me just mention the calculus. The small change of z would be dz, derivative of z with respect to, and you can ignore this part if you want, ignore dx times the small change in x. By delta, this is small change. So the small change in Z would be there. So our simpler way to say it is that Z final or Z next would be equal to the current Z. And suppose you made a small change in times a small change in X. So you realize that this is this. Now, and then the high order terms, which you'll forget it in Taylor expansion. But for very small values, very, very small, that's why I use the word small, so that the higher order terms disappear in a Taylor expansion, people say. We won't go into that Taylor expansion. Let's ignore that, right? Because they'll vanish. Now we look at this term. How do we compute the derivative of Z? So here comes a bit of a rule. You say that let's see how changes propagate, right? How change in this. So you realize that this is pretty complicated, right? If I write a function, let me just write something. T, let us say that T is equal to sine square of X. G is equal to e to the minus t square, gt. And f is equal to f of g, f of this, I think I should use the word t. T of x was y, isn't it? Y is equal to this. And then, so this f of g is basically equal to, let's write something even more complex here. Let us say that it is equal to, let's say it is equal to g square, right? G square. So now you could write the whole thing in a complicated way. You can say that z is equal to, what is it? It is equal to, first of all, sine x squared, e to the minus sine, well, let me just write it as minus t because there are too many things here. E to the minus sine square x, right? And the entire thing squared, right? Or squared, or maybe I'll just make it simple. Let us say that it is equal to 10 times this. Just let's write it 10 times this. We'll make the last one a little bit simple because I don't want to write a complicated expression here. Right. So now you realize, or maybe why not make it complicated? Let us say that this is equal to, for lack of something better, I will say cosine of g. So now you have a very complicated expression. It is equal to the cosine of the e to the z. Now, how many of you feel that you can just look at it and tell the derivative, dz dx, right? This is exactly the sort of problem you hope you're not asked, because it's been a few years since we did differentiation and integration. So what I'll do is I'll take a little bit of a time to brush it up and give you an inkling of how very easy actually it is to solve it. See, most of us remember basic things. So let me just make a little box, memory box. And typically you can look it up. The derivative of, so I will write functions. Derivative of x is e to the x itself. Derivative of x to the power n is n times x n minus 1. Right? Derivative of sine x is cosine x. Derivative of cosine x is minus sine x. Suppose these are very basic rules that you may remember. And let us say that we just remember these few rules. The question is, can we use that to solve this problem, this much more complicated problem? So one way that you can solve it is to just ask this question, how can I make this part, how can I make this part, this complicated part, nothing but this part? Look up into this table. Right? Easy question. So I have a joke here. It's a little bit tangential joke, but I'll make it here. For my children, when they were in high school and middle school, they used to watch a TV show called Psych. Some of you may know about it, or your children may be watching it, Psych. Does it ring a bell with any one of you?
Yes, Asaf.
It does, right? So I'll just give you a little bit of a background. So there are two characters, young characters, uh, Sean and Gus. Gus is the sensible guy, and Sean is the one who has very good observational powers to solve various crimes. But uh, he is, in other ways, not very intellectually endowed, right? So now, once it so happens that they have to stand for a mayor's, they have to campaign to be a mayor of a city, Santa Barbara. Why? Because they're trying to solve a crime and they start polling against the leading candidate who they suspect is implicated somehow. So people now start coaching Sean on how you deal with the press and how you deal with people. So one advice I remember from that, which is very, very good, it says that in politics, there's a very simple way to be confident. Never ask the question that you, never answer the question that you were asked. Instead, answer a question that you wished you were asked. Right? So, in other words, always answer a question, not the question that you find hard or you don't want to answer. Find some related question that you would actually prefer answering and answer that instead. Right? And it sort of works. And if you notice, that's the constant exchange between journalists and politicians. Uh, when asked a question, politicians will always give, not answer that question. They'll quite often, not always, but sometimes answer something else. And the job of a journalist is to bring the politician back to that question and pin him down or her down to answering that question. So there is some flavor of that. So I'm going to use that reasoning, right? That how can we answer this question by not answering this big complicated question, but answering something that we know we can. So let's look at this problem. So suppose I could write z is equal to just cosine of, what was it? W, cosine of uh, W, right? W. So here, can we take the derivative of W? If instead of finding the derivative with respect to X, our job was to find the derivative with respect to W, could we have done that? We could have done that. We could have said minus sine W. Would you agree? Because all we have to do is look up this table that we have, and we realize that here is it. Here is the answer sitting there. So here is the function, and the derivative, f prime, right, the derivative. So this is easy. Now let's ask the other question. What is W? W happens to be e to the minus sine square x. Well, that is complicated. But again, let us simplify it and say, what if it was just e to the minus t, okay? Some variable t. And then could we have solved for t? You would say W is equal to e to the minus t. This is easy. dw dt would be minus e to the minus t. Right? Once again, you look up the table and you say, so let us hold on to this partial results. This is true. And then we can ask ourselves, so what is t here? It turns out that t is sine square x. It looks complicated. So let us say that this is actually sine, write it as sine x square. So let me create some other variable y. Is that appropriate? Or maybe I'll just, I don't know what I called y as u. And you say that u is equal to u square, u being sine x. Now, is this again is solvable? This is very solvable. You can say dt du is equal to 2u. And so do you notice that at each point, we are not solving the problem that we were initially given. We are chipping away at the problem one little bite at a time. We are only solving the problem that we wish we had, right? In a simpler way, the parts of the problem. And we make progress with that. And finally, you say that, all right, now what is u? U is sine x. So this is another result. And so u is sine x. And it turns out that, yes, now we can solve it in one stroke. And this is a cosine x. And so now you say that, see, I have a whole set of partial results. I have dz, dw, I have a dw dt, I have a dt du, and I have du dx. And it turns out that here, a calculus sort of comes to your rescue. It says that dz dx, the initial problem that you wanted to solve, is nothing but the product of all these partial, steps chipping away. So you have, in essence, chipped away at the problem uh, piece by piece, and you have solved it. Right? So you would say that this would be cosine x here, and then you would say dt du is 2u, right? So that would be 2. Now what is u? U is sine x, 2 sine x, right? Then comes dw dt. What is dw dt? Minus e to the minus t. So minus t is sine square x here. And then, so this is one more factor. And then comes the final w. W, oh no, this dw, I think we took care of this. Did we take care of this? dw dt is this. And dz is minus sine w. So minus sine of w. But what is w? W is this whole thing, e to the minus sine square x. Right? So you can just multiply all of these things and you would know what your answer is. Right? So I hope I haven't made a mistake. I might have made a mistake somewhere along. Yeah, this is a sine of this entire thing. Sorry, sine of this entire thing minus sine of the entire thing. So this minus minus cancels out. And then you have this complicated product here, sine of e to the minus x squared and so on and so forth. And so what you did is you found a very complicated derivative. Do you notice? By chipping away at the problem at a time. Now you would say, well, why would I do that? Well, the answer to that is now you go back to your initial update rule and you say, well, how much will, you remember that we said that the next value of z is, if you make a small change in x, it is the previous value of z plus dz dx, isn't it? And we just computed that, and we of course knew the previous value of z. And so what happens is we have figured out times delta x, of course, the small step. Right? So you notice that we can choose how much of a step we take. We know the previous value of z, and so we know that if we take a small step, how much will z change? Do you see this, guys? Or another way to say that is delta z is equal to the derivative dz or dx, which was a complicated thing, times delta x, right? So guys, any questions here? This is just a sort of a review of the kind of calculus we have done a long time ago. Am I making sense, guys? Anybody who has a question? If not, this was the only preliminary we needed to make progress. Since no one is asking questions, can somebody confirm that this was straightforward to understand? One of you, speak up, please.
Yes.
Okay.
Yes. Yes.
It's a straightforward. So this is the chain rule, guys. Huh? Give me 1 second. So now comes the question that how do we relate this to our neural network? In our neural network, we have, let's take a situation. We know that we have layers upon layers of nodes here, right? You have input, you have lots of layers and layers of nodes, right? And all of them have complicated, lots and lots of nodes are here. I'll just put dot, dot, dot. And finally, you have some output, y hat. Output leads to the loss function, right? Now, this loss function is dependent on the weights at each of the layers, right? There are a lot of weights at this layer, so this is at the layer 1, layer 2, layer L. Lots and lots of weights will be there, right? So depending upon how many nodes there are, and each node will have multiple inputs coming to it, and so on and so forth. So there will be quite a few weights here. And you ask yourself that if we want to do gradient descent, what do we do? we take the value, any particular weight. Let us say that some weight, now how do we think of a weight? At this moment, just think of some simple weight. Let this be an arbitrary parameter, or arbitrary neural net parameter, right? Some weight, parameter, weight. I'm considering bias as just W0, parameter, bias or weight. Anything, I'll just use the notation W. So you remember that gradient descent said what did it say? That W next, the update we make when we want to improve or we want to make the machine learn and make less mistakes, is this W, the current value of W minus the learning rate, right, times the derivative of the loss function, partial derivative, the derivative of the loss function with respect to W. Now you notice that I'm using a notation. I'm not using D. I'm not using DL dW. I'm instead using D, this funny symbol, partial. This is called a partial. And this acknowledges the fact that the loss function doesn't depend on just this weight. It depends on all the other hundreds of weights. If any one of them changes, the loss would change. So this contributes to the loss. Whereas in one dimension, if y is, like when you say y is equal to a sine of x, then y depends only on x. In our situation, y depends on, this loss depends on many weights. I just took an arbitrary weight, and this is our gradient descent rule. So far we are together, guys. We did gradient descent, and this is what we need to do. Now comes the question that how do we compute this guy? This guy is the big problem, actually, because it's not so easy to know. And it begins to look like a problem because, see, if some weight here changes, in the first layer changes, W1, right? And it may belong to some node. Let us say that it belongs to node I, and in node I, so let's say ith node in the first layer, right? So let me say layer 1, it is a node. In this node, suppose their parameters are x1 all the way to xn. So what happens is each of these will be I1, In. So in other words, any one weight will be Ij in the first. So you notice this peculiar, you need to tell, given a weight, which layer it belongs to, which node it belongs to, and which of its inputs coming to it, you're going to apply that sort of a weight to, right? So if you think about it, the Z of I, the sort of accumulated result would be the W of I in the first layer, and I'll just use this bracketed term. It doesn't mean that the power, it just to signify that you don't raise Z to the power 1 or 2 or 3. It just signifies the layer. In the first layer, suppose you take the ith node for ith node in layer 1, right? So this Zi would be this times what? J xj, isn't it? So in other words, let me just write it down. It will be equal to Wi0 plus, which is essentially a Bi of the first layer, the bias, plus x1. Let us say, if we can get this right, x1, actually, let me space it out a little bit. So it would be Wi1 x1 plus Wi2 x2 plus, and we can go here. So suppose an arbitrary xi, j is there, xj, right? Plus all the way to xn, dot, 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 you will get to WIN XN, right? Assuming a n dimensional input to this first layer. So you would agree that this is the linear, this is the affine transformation we talked about, and the output would be the response, the output of the first layer would be, which is what? It is nothing but the y hat output is nothing but of the first layer of the first node in the layer would be I in the first layer, the ith node will produce an output which is nothing but the activation function, and I'm using sigma for activation function, of Zi. So does this make sense, guys? So in other words, this ith node, I in layer 1 is made up of all of these weights coming in. So Zi layer 1, and this is the activation of Zi in layer 1 times, and that becomes the output, right? I could write y hat. Maybe I could, we are used to writing y hat, we could write, but y hat is the ultimate one at the very, very end. We will just write A here. A of the first layer, the output of the first layer from the ith node is this. So does this make sense, guys? Does this look very familiar so far? Okay. So from this, let's come up with a generalized notation. We will generalize and write a notation, which we will say that in our notation, weight ij of layer L, right, would stand for, interpret as follows. Interpret as follows. It is the weight associated with ith node in layer L and input component xj, whatever the jth component of that is. Does this make sense, guys? So we will take this as our notation. Do you see how simple this notation is? But if you think about it, you realize something very interesting. This big W, what is its dimensionality of it? Like, how many dimensions does it have? If you look at a neural network, how many? It will have many, many layers, isn't it? Right? So let's think about it. Let's think of a neural net which has, I will just take 2, 3 here and 2 here. And let us say that the inputs are coming here from something or the other. So you realize that here I have, let's say that there are 2 inputs, x1, x2. So now I can write this. This is the first, second, third, first, second, third. Let me just name these guys. Node 1, node 2, node 3. So you would agree that this is W11 of layer in the first one, and this one is W, I don't know, 1, 2, and this one is W21, this is W22, this is W31, this is W32. Do we see all these weights here, guys? And besides the weights, of course, we have the biases also. W0 is equal to, W0 of the first one, W0 of the biases are fixed, W0 of the second, well, not fixed, they also are parameters, they change. W30, right? So do you see how many things we got? If we write it, you're already looking at, just looking at one node, you're looking at a vector, isn't it? So suppose I fix the first parameter. W layer 1 and the first one. So you know that it itself is made up of W1, 1, W1, 2, W1, 3, and not to mention the bias term, W1, 0. It is like this. Likewise, you have W2 of the first layer. That will look like a vector, W2, 0, W2, 1, W2, 2, W2, 3, right? And you could do that. So what happens is you get this, and now you have W3 of the first layer. So putting W1, 1, W2 node of this weights of the second node and weights of the third node together, what do you get? Suppose you put them together, you get this giant, what is called a matrix. 1, 0, W, 1, 1, W, 1, 2, W, 1, 3, W, 2, 0, W, 2, 1, and we can fill it in W, 3, 0, all the way to W, 3, 3. Do you see this, guys? Huh? And this is still in the first layer. You could say that the matrix of weights for the first layer looks like this. Are we together, guys? And so there will be a matrix of weights for the second layer also. W2 would also look something similar to that, right? And W3 will also look something similar to that. Are we together, guys, so far? Any questions, guys?
No, it looks good.
Okay, so these are your weights. Now let's see, we will look at something that I would call the forward pass. In this deep neural network literature, you call it the forward pass. Forward pass. It is that, suppose you have a neural network, layer 1, with layer 2, layer L going here. And you take the X vector and you multiply it through each of these. It will take you a while to realize that, how do I do that? Right? Suppose I have X1, X2. So we have X1, X2 here, right? So how do we do this multiplication? What is the output of the first node? If you look at it, X1 went in, X1, X2 went in. Let's look at the first node of layer 1. Now, what was it made up of? If you remember, this is made up of 0, 1, 1, 1, 2. Are we together? It is made up of these two things. Actually, did I? No. Why did I bring in? This wasn't there. I apologize. And W3 is equal to 3031. Why? Because there are only two of those. So now, suppose I take this input. You have this matrix. This is called the weight vector. And you take the input vector. Input is X1, X2. Suppose I put a 1 here. Now, people now see what happens if you take the product of these two. The product is, you take the pairwise product of these two. So this vector, and in notation, we can say this is W transpose X if you're thinking in terms of matrices, vector notation and so forth. But let's just look at it in simple terms. So if I multiply these two, you would agree that this becomes W11 X1 plus W12 X2, which agrees with a notion of what it should be. This is the Z. Right? Z is equal to that. And the output A of the first one, of activation function, I'll just remove the subscripts for a while, of the first one, Z1, let's say, is sigmoid of Z1, right? So all we did is we multiplied this. Now generalize it to this big matrix. What happens with this matrix? By the way, there is no third element here. Right? Now see what happens if I do this. I took 1, x, 1, x2, and I multiplied by W10, W11, W12, the second node, node 1 of the first layer. This is the node 2 of the second layer, 20, W2, 1, W22, because there are 2 inputs, and W third is a 30, W31, W32. You realize that I can multiply, I could find the output of each of these things by doing it together. And when I do it, what I expect to get as a result is Z1, Z2, Z3, isn't it, guys? And Z1, Z2, Z3 is the output. And then you apply the sigmoid to that, and you'll get sigmoid of Z1, sigmoid of Z2, sigmoid of Z3, right? So this is your A1, A2, A3 in the first layer. So far, guys, am I making sense? I'm not doing anything complicated. I'm just doing basic multiplication, right, to see what is the output from the first layer. And I know that the net output from the first layer is basically these activations, A1, A2, A3. Right? People call these matrices and vectors and so forth, writing data together like this. But let's stick to simple terminology. So what we realize is that if we take the weight matrix of the first layer and you multiply the input to the first layer, let's say that whatever the input is to layer 1, right, transpose, and I'll just put a transpose here to simplify that. In matrix notation, you would call it transpose. You will get, and you apply the sigmoid of this, you will get the A vector, right? A vector being A1, 1, A1, 2 of the first layer. And this is, of course, of the first layer, the first layer, A2, A3 of the first layer. So far, I hope, guys, I'm just creating some fancy notation to help us along, but nothing great. You know that we have to multiply all of these weights together, isn't it, guys? But now,
Yes.
how do I find the output of the second layer? Well, it turns out that the X went in, and this A vector from the first layer came out. And as far as the second layer is concerned, A vector is the input to the second layer, right? These activations are the input to the second layer. The second layer doesn't know that it's a hidden layer. As far as the second layer is concerned, it is getting inputs, which is this, A1. And this is the input vector. And so it will do exactly the same thing. What would be the output here? A2 vector would be, basically, if you use this notation, it would be sigmoid of, what will it be? A1 vector transpose times the weight vector, the weight matrix of the weight matrix of the second layer. Right? Basically, you're taking the same kind of dot product. In other words, what you're doing is, suppose, and I'll just write it for the second layer to illustrate it. Let's say that the second layer has whatever number of nodes. Let's say that for the second layer, there is a first, so a second layer, right? This is it. And I'm just writing it in the notation here. Now I'll go back and put this 1, 2, 3, 1, 1, 1 to simplify this is the first layer. Now what happens is that we are complicating the notation. Unfortunately, you see in neural networks, you see this complicated notation. But I wanted to emphasize that this is actually very simple. It is just a way to remember in this maze of weights, which layer and which node does this weight belong to. So now we can say of the first node, 0, 1, 1, 1, 2, whatever number that is there, let's say k nodes are there, 1, k, right? And this is all for the second layer, etc. And now you could do for the next node and for the next node, you'll get the matrix W2, second layer matrix, second layer weight matrix. And the only thing we know is that the input is A1, A2, A3, 1, right? This is what is going in. If you look at this picture, where is our picture? Right? Here, 3 activations are coming out from here. This is A11, this is activation from the first layer, A12, and the second node in the first layer, and the activation from the first layer, node 3. Do we agree that these are the 3 inputs to this layer, the second layer?
Asif,
Yes, go ahead.
this assumes that your matrix comes from a fully connected layer, right?
Yes, at this moment we are looking, let's look at a fully connected layer. Right? So we are
Okay.
looking at a dense network. Just imagine that the outputs are all going into the next layer. And then later on we'll argue that it doesn't make a difference whether it's fully connected or not. Dropouts, etc. They don't affect the basic mathematics. Right? So now looking at this, therefore, what can we write? This is just a fancy way of saying that the activation, and what will come out of all of this, multiplying this will give us the activation vector from the second layer. Activation vector of the second layer is therefore equal to the activation vector of the first layer times the weight matrix of the first layer, isn't it? We write it. So now we're getting the hang of it. This entire thing is beginning to look like a sort of a simple thing. We can say the activation from the first layer was the input vector, right? And obviously I put a dot here, but actually you can think of a transpose. Maybe I'll put transpose. Think of transpose as just multiplying the way that we are multiplying of the first layer. A2 is equal to A1 of the first layer times the weight 2, and again the transpose. A3 is A, well, 2 transpose and weight of the third layer. And now, do you see, suppose I have n layers, L layers, what do you conclude? A of the L layer is equal to the activation of the L minus 1 layer times the weight matrix of the Lth layer, right? And so you start from the input. So what happens is X vector goes in, A1 comes out, right? The A1 vector comes out of the first layer, that produces the A2 vector activation of the second layer and keeps on going in to the activation vector of L minus 1 layer, and that produces the activation vector of the last layer, which is our result. Do you see this chain, guys?
Yes, Asif.
And do you now see that this is just nothing but a lot of multiplications? Because I could, for example, I could squeeze these two and say, therefore, A2 is nothing but, what is it? A2 is nothing but X transpose times weight matrix 1, right? And the whole thing transpose times W2, right? And now I can keep on substituting all of these values. So you're looking at the input times lots of multiplications. So you say that this is your forward pass. The forward pass is just crazy matrix multiplications, but easy, hopefully. Like, so long as you don't get lost, which what this notations mean, what it means to say Lij, you know what this means, then all you have to remember is that is this one expression, namely the
Asif, one second. This is Chandar here.
Yeah.
You made a slight error in that. I mean, you shouldn't be doing a whole transpose. Actually, what you have on the left-hand sides,
Mhm.
they are all the transpose itself. They are A1 transpose, A2 transpose. So
Oh,
that
right.
it-
They,
because
this,
that is how the I mean, just because later on when somebody is looking at the notes, they shouldn't get confused. I mean,
Yes,
it
yes.
is A1 transpose, A2 transpose,
E
and all.
times this, A1 times this. You're right. So the transpose is in the first one only. Absolutely. Thank you. Thank you for.
So the matrix multiplication also, when you are doing this chained multiplication, you don't have to do the
You need to
transpose.
do transforms. Excellent. Yes, you just need the transform of the input vector. And after that, it is just straightforward. Yes. And one more thing actually I missed. There was one more mistake, which is that I forgot the activation functions here. Uh, where am I? So let me put it in a red color. Sigma, the activation functions, right? So what happens is that, so the general rule, we can write it as, and the activation function I forgot, is equal to the activation of the product, right? Weight products. So let me just write it in big bold things. The output of the nth layer is equal to the sigmoid of the output of the previous layer times the weights of this layer. And weight is, I'll just write it as a big bold to symbolify that this is a matrix. Are we together, guys? All we are doing is continuously multiplying, right? So forward pass is just a bit of multiplication. So long as we know the weights, we are able to multiply. So what happens when your neural network is fully trained? When your neural net is fully trained. Thanks, Chandra, for pointing that one out. So when you're, what did I just write? Neural net is fully trained. All you have to do to get y hat is basically the activation of the last layer is equal to, and then all you do is x goes in and you keep on multiplying and then you get this answer. It is just multiplication. But it does raise the question, how do we know the value of the weights? In a fully trained network, the weights are already learned, the best weights, the best parameters have been learned. So how do we learn it? The answer to that is, of course, gradient descent. But gradient descent is a little bit complicated in our situation. See, the activation of the last layer depends on the activation of the previous layers times the weight, right? Which itself depends, which is a function of one layer before it, is it? So does this remind you of this peculiar thing that we were talking about? Let's go back. Where are we? Yeah. So guys, does this sort of remind you of this? Z, the last layer, is a function of the previous activations, which is a function of the previous in the previous, and ultimately in the beginning is the input. And what you're basically trying to say is, how does the entire network depend or vary with respect to either the inputs or the weights of the system? So if I want to find out, what do we want to find out? Let's go back to our gradient descent rule. Our gradient descent rule was, just to recap, gradient descent. Now we'll write it in this fancy, with this, all of these notations. Remember, this was that we need the gradient. How much does the gradient change if I know, or sort of, let me just write a partial derivative to emphasize that. Partial derivative of this, let me write green symbols. Partial derivative of this with respect to some layer L, weight ij of some layer. Now, you know that if I know that, then in that layer and for that weight, I can make the adjustment. The next value is the previous value minus alpha. What was alpha, guys?
Learning rate.
It is the learning rate, right? So we will, this is the learning rate. So the only thing we need to know is, let us figure out a way to compute these changes layer by layer we just need to compute what? Alpha is our decision, isn't it? We decide, let's say that we say 0.01 by choice, isn't it? We may choose some value. So, and you have fixed it. The previous value of weight, of course, you know. All you need to know is in the learning process, you need to know this. So now there is, interestingly, there is a very descriptive name to it. It is called the backward pass. The backward pass of learning. This is where the learning takes place. So you do it only while learning, not while just making predictions, not at inference time. It is only when you want to improve your weights because the loss is still unacceptable. The errors are still unacceptable. So how do we do that? So what I will do is, sorry, I somehow went back to a previous lecture. Give me a moment, guys. I didn't know how I managed to do that. Oh, there it is. I figured out how.
So is it Wij to the power of L minus 1 previous term?
No, not the power. It is not the power. It is just layer. It just talks about the layer L. Once again, it is not the power, guys. See, if W cube would have been the power, third power, I deliberately put it here. This is third layer.
The previous layer, like L minus 1 layer, or is it L only?
What do you mean by L minus? Oh, this derivative it is L. Remember, for any parameter, so think of it like that. Forget these weights. Let's go back to our previous machine learning. Remember, we used to say that
So the weight of Ij,
yeah.
L layer equal to weight of Ij, the previous layer, no?
Yes, that is true.
One layer.
Not the weight, the activations. Let's go back again and see what happens. Input X goes in, you have some weights. It will multiply with these weights to produce the activation of the first layer. That will hit the weights of the second layer to produce activation of the second layer. And it will keep going onwards till it produces the final result. Oh, I should remove the transpose from here again. So it will produce, this is your final, ultimately, at the end of your network, whatever is the last activation, that is your result, isn't it? You're just multiplying in the forward pass. Am I making sense?
I think Harani's question, if you go back to that last expression that you showed,
Yes.
the way I was interpreting Harani's question is, so what you've shown here is essentially the computational pass where the weights are adjusted. So the weights of the Lth layer is adjusted based on the weights minus the loss function, basically dou L by dou weights of that, right? That's why it's the adjustment that you're talking here.
Say this out aloud. Huh? You say that the weight, the new weight, any one weight, some arbitrary weight, would just happen as, give me a second, guys. This is some arbitrary weight in some layer, some arbitrary weight in some layer. In whatever layer it is, in the Lth layer, how would you identify? What is the coordinates of it? Like, where does it live in this space? You would say that it belongs to the Lth layer, and so you would say it belongs to Lth layer, ith node, and jth weight of the node. Weight of the, or weight, jth, weight associated with jth input to that node. Do we agree, guys? Huh? This is just the notation Harini, is this clear?
Sir.
Right?
Yeah,
And all
question.
thing. So it is just some parameter. Think of it as beta. Now, if you just imagine that it's beta, you remember what was our update rule for beta? How do you find beta next? Right? It used to be the previous value of beta minus alpha times the gradient of the error, right? Gradient of the loss with respect to beta. Do you remember? This is our gradient descent rule. We did in the previous workshops also. Do we remember this, guys? Huh? So in other words, in a parameter space where a beta is the axis and this is the loss, remember, how do you make a step, a better step from here? How do you step back? How do you make this step? You say that this is the rule, isn't it, guys? Harini, is this clear? Does it remind you?
Yes, sir.
Okay, this is it. It just so happens that the beta we are talking about, there are many betas in a neural network. It's just complicated. It is ij of the Lth layer. And so you say that the wij of the Lth layer, the next value of it is the value that was there before we learned, before we applied our a bit of learning minus alpha, before we did the gradient descent step, times the loss, derivative of the loss with respect to exactly this, the existing value of the weight. Right? And therefore, this becomes the more detailed, this becomes the more sort of a complicated way of writing the same thing, realizing that there's so many betas and it needs three indices to notate it, I, J, and L, to give you the coordinates of any one of the parameters of weights. So far, so good, guys?
Yes, sir. Next was missing in the previous equation, so I got confused.
Okay. But now are we clear?
Sif,
Now it's better. Yes.
Good.
you say that the next would be your value in the next step. Is that correct?
Okay. So see, what are you doing? Go back to our example of resistors with a distortion function. This is your beta. You made a you put some voltages in x1, x2. You got some current. This is not what you wanted, right? So you have an error. Now, how can you fix the error? You need to look at the loss here, the error here, and you have to say, hey, I need to decrease this. Need to decrease the loss, right, or the error. Because machine learning is, the learning word in machine learning simply means decreasing the loss, the mistakes. You want the output to be what it really is. So this is your I hat or Y hat. Let us say Y hat is different from Y. And this gap is the mistake. And what you want to do is the total mistake that you make, you square it and do all sorts of things, average it. The average squared mistakes is your loss, total average loss. You want to minimize that. So how do you minimize that? You can't change the input, but what you can do is you can improve this. Beta goes to beta next, improved, the improved value of it. So what you do is you want to move the rheostat a little bit and you want to say, okay, I want a better beta. And this loss is informing me how to do it. I just need to take this step. The next value of beta should be my current value minus some learning rate times the gradient of loss with respect to this parameter beta. Are we together, guys? No?
Yes.
Yes.
Sanjay, we got that. So
Yeah.
it's as simple as that. So see, that is all it is. When we use fancy words like AI, you know,
Correct. I was just trying to relate it to, when we look through the the epoch and the steps.
Yes.
Trying to look.
Yeah. So we are in the learning step mode.
Correct.
It is the backward pass. See, the forward pass, what did we do? We just computed the output. Output produces a loss, right? Given the output, there are mistakes, it gives us the loss. Now, if we can find the gradient of the loss, we are fine. We can do this, right? So let me put it this way: the forward pass will do what? Given x, it will produce y hat, and therefore it will produce the loss. And then the backward pass needs to this. Backward pass would be, which we are getting to, is basically updates. Update of weights using gradient descent. But before we do gradient descent, there is one big problem. We need to first find. Guys. So yes, please keep it muted. So far, guys, are we together? It's very simple. Now comes the complicated. Guys, why don't we take a 10 minutes break?
Sorry.
Let's take a 10 minutes break, guys. Is that okay? We'll meet at actually 15 minutes. 6:45. Let us meet at 10 o'clock.
Sorry, you can mute it.
I don't know who it is. Yeah. Yes. All right. So, guys, I've muted everybody. So I don't know. My question is, are you guys up to a break, a 15-minute break before we continue?
Yes.
Or should I continue?
Yeah.
Great. All right.
Okay, either ways, I see if you want to wrap up, that's also fine.
Yeah, let's take a 15 minutes break. Some participant is having distress at home with the child, so it will give the person some opportunity to take care of that. Let's meet.
Okay.
I'll pause the recording.
Sir, can I ask a question?
Absolutely.
Sir, um, I'm getting confused a little bit with Markov chain Monte Carlo. Why it looks like that?
Markov chain Monte Carlo. Okay. Uh, it's a little bit of a digression. So did I pause the recording? 1 second. Let me make sure the recording is paused.
We are not recording, sir.
It's not recording. So let me, and I will take another screen. So see, Markov chain Monte Carlo is based on two. I suppose you want to understand why we do the funny things we do.
Sir.
Right? See, it's based on two ideas. One is the Markov chain. Right? Markov chain, what is it? It's a series of steps,
Sir.
right, that have a Markov property. I'll tell you what a Markov property is. Suppose here is a place. Something can enter through, and somehow a thing can enter. Let's say that one atom enters here, and this is filled with a lot of atoms, right, or something like that. Now this atom, for whatever reason, because it bounced across other atom, or usually the way you think of it is as a drunk person. This drunk person can take a step in the forward direction, can take a step in this direction, can take a step in this direction after that, can take this step, any random step. So you would agree that whether he enters from here or from here or from here or from any arbitrary point, he enters this landscape. So long at any given point, suppose he's here, location is XL. His location X plus 1, the next step depends only on the previous step. It doesn't depend after a little while on where he started from. You just,
Yes, sir. Yeah.
after a little while, he'll be all over the place. He would be scanning all over the place. So that is a Markov property of something, which means that after a little while, there is no history to it. The only thing that matters is where is the person now, and that alone will determine the future of the person. Right?
Okay.
So that is the Markov. When his path is you have Markov chains. Now comes a property of Monte Carlo. Monte Carlo just says that suppose you have a very complicated function. Let a function be, and I'll just take one dimension. Function be fx, and I tell you that fx is this very complicated function. It is, or maybe I won't let it go in the negative direction. Let me keep it positive only. This, and let's say that the very complex function. And I ask you this, find the area from A to B, right, which is this area.
Yep.
Then you say that, okay, this is easy. All I need to do is area is the integral from A to B of fx dx. So this is a typical calculus problem. Now, one of the great problems in mathematics is, while you can differentiate any function which is given to you in closed form, like for which there is a formula, unbelievably, most functions cannot be integrated. The few functions whose integral you can calculate in a closed form are the ones that are there in your textbook. But if you go beyond your textbook and ask how many, when you go through a calculus course, very easily you may come under the impression that given a function, you can of course find its derivative and of course find its integral. But actually that's not true. Derivative part, yes. Integral part, you can't find the integral. Even derivative has some caveats, but roughly speaking, yes. Integral, no, you can't. In fact, most functions cannot be integrated. The sum total of all functions, I mean, people who are well versed in applied math, they know all the functions that can be integrated. And in fact, you'll find it in the back of your typical engineering math textbooks. Most of those integrals you'll find. Right? And other ones, you can't. And yet real life comes with situations like this. You get a very complicated function and you have to find the integral of it. Why? Well, it's a part of machine learning thing, Bayesian machine learning thing. And I wouldn't go into, it's sort of the evidence part of it. That at some point in the denominator, there is an integral, right? And I won't talk more about that. It's a thing. Let's not get more confusing. So now the whole question is, how do I integrate something? So suppose I give you this, like sine of e to the, or cosine, like I took this function a little while ago, right? Something as bizarre as cosine of e to the minus sine square x, and to make it worse, let me divide it by x2, right? Yes. And while we are at it, why not add a couple of more things? Tan of that. You realize that by the time you figure out how to integrate this, the cows will come home, and you may discover that you can't integrate it after all. You don't know how to do it. You'll get stuck. All your techniques, your integral by parts and this and that, they will all fail after some time. It may or may not, I don't know. This one looks too simple. You might be able to integrate it. But generally, most functions you can't. And very simple functions, like for example, a bell curve is given by e to the minus x squared over t. Here, the sigma is mu is equal to 0, sigma is equal to 1. A standard bell curve, right?
Gaussian distribution.
Gaussian distribution. But believe it or not, you can't integrate this. Suppose I say, find the integral from minus infinity. Why am I not able to write it? One second. Yeah. So find the integral from minus infinity to some value x. So that becomes, or some value t, let us say. Okay. So that integral would be some function of t is equal to minus infinity to t of this same thing, right? 1 over 2 pi square root e to the minus x squared over 2. So you say, well, this looks like a classic problem you would give a high school student doing calculus to solve. And it comes as a surprise after a little while to realize that you cannot solve it. Solve it in closed form. Like in the way we think of solving calculus problem, right? You can simply not solve it. So what is the trick to solve it? So here's a trick that you can use. What you do is imagine that you wrap this data in a box. From A to B you want to do, and you know that the data rises up to this level. This is your max, some level. Let me call it C. So the area of the red rectangle, is essentially AC times AB. You agree with that? The base times the side is the area. Now you do this interesting game. You start throwing darts at this board. You throw a dart here, 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 here. You just go and take random points, lots of random points, or the visual metaphor is you throw a dart at this dartboard. And for each point, you ask this question, let me write it in green itself, is below F or above. Right? So for example, this point, is it below the curve or above the curve?
Below the curve.
It's below the curve. So every time you get it below, you treat it as a 1. If you get it above the curve, you treat it as a 0 for below and for above. So let's say that you throw a large number of darts at this board. Let's say you throw n darts, where n is 1 million. I'm taking a rough number, right? 1 million darts. So now tell me, what proportion of darts will fall below the curve?
Equal to the area under the curve.
Yes. In fact, the ratio of the proportion below the curve of the total proportion below would be equal to area of the curve over rectangle. Now, rectangle area is trivial to calculate, right? You just built a rectangle, you know the limits. B minus A times C minus A, isn't it?
Yes. Yes.
This is it. But now, this answer you can experimentally observe, right? Because you threw so many darts and you kept a count of how many darts hit below the line. And therefore, you can compute this area, which is nothing but proportion below times the area of the rectangle.
Area of the rectangle.
Right? And this is a remarkable truth, actually. If you really think about it, it's astounding. You threw random darts, you use randomness to help you do an integral. Isn't that amazing?
Yes.
Right? So this thing is called Monte Carlo.
Yes.
The Monte Carlo process of solving. It turns out that a lot of complicated mathematical problems, if all else fails, you can always hope that Monte Carlo or some variant of it will take you through. Right? And so that is the Monte Carlo part of it. Now, when you put these two together, along with Markov chain Monte Carlo comes from this fact, there is an algorithm called the Metropolis algorithm. And again, we are reaching the end of our discussion, so I'll keep it below. Metropolis algorithm. This is, if you Google the most important algorithm of the 20th century, you will realize that the answer is this. Isn't it a bit of a tragedy that most computer science curriculums don't teach you this? Try Googling it out, the most important algorithm of the 20th century, and you realize this. So what this says is something very interesting. It says that, and I'll give you in terms of machine learning, I'll tell you. So, you know, you are in the hypothesis space, right? Suppose this is W naught, this is W1. And any one point represents, you know, suppose you have data, it represents the intercept and slope. Intercept, slope.
Asif, do you want to start recording?
No, this is just a digression. I'll finish this and then I'll come back to that.
Okay.
Suppose this is the parameter space, you know, the hypothesis space. So this space, what you do is you start with a guess somewhere, right? So this is your drunken fellow. And you do one thing. In this space, you take any arbitrary point. Let us say you take this point. And it is almost like every time the drunken fellow wants to take a step, he may or may not take a step. What you do is, you look at the data and you ask this data, if I chose this as the hypothesis, this new point is the hypothesis, you know, each point in the hypothesis space is a hypothesis. In real life, it is some line. You ask, could this hypothesis have produced this data?
Yeah.
More likely to produce this data or less likely to produce this data compared to this hypothesis where you are? If it turns out that this is less likely to produce the answer, then there is a choice. You just toss a coin.
Yes.
And let's say that you toss a coin, heads or tails, right? If it comes out heads, you still go here, even though this hypothesis is less likely to, the data doesn't favor this hypothesis. Still, you sort of take the step here. On the other hand, if this point is more favored by data, you definitely take a step here. So it's very interesting. If a point is favored, you definitely move towards it. If a point is not favored by data, then you toss a coin. You may still go with a small probability to that point. Are we together?
Sure.
And what you do is you keep moving around all over this space. And at the end of it, so imagine that this drunk guy has shoes, which has some black color attached to it, right? A black color. So as the person walks through this hypothesis space, at each point, at each step, just picking a random point and asking, should I jump to there or not? And then if if the probability is less, likelihood of the data producing that point is, that hypothesis producing the data is less, then you still toss a coin and you may still go. But if it is more, you definitely go. That's all that the Metropolis algorithm says.
Yes.
And the most amazing thing is you will wake up in the morning, that is after a sufficiently large amount of time, you will notice that the places where that guy has spent most of his foot, the color is darkest, the shoe color is darkest, or in other words, the fellow has spent most of the time, most time is actually the best hypothesis. He'll repeatedly go through that point over and over again, gradually. Right? He'll spend far more time there throughout the night than at other places. And so all you have to do in the morning is just see, okay, where did he spend the most amount of time? Wherever he spent, that point is your best hypothesis. In other words, in our notation, that is your W star. Right? And so what you have done is you have used Markov chain Monte Carlo to solve the problem. Do you see how the ideas of a Markov and Markov chain, his path is a Markov chain. And the Monte Carlo means you randomly are throwing darts and saying, should the drunken man go there or not? Right? And taking a step. And then the Metropolis algorithm just tells you whether he does or does not take the step. So you put these three things together, and in the morning you wake up, let the drunken guy roam all through the night in that landscape. You wake up in the morning and you just look for the darkest place where he has left most color from his shoes. Or in other words, you spend most time. And that is your answer. And to do it like this, find solutions to problems like this, is Markov chain Monte Carlo. That is why it is so powerful. It helps you solve very, very complicated problems.
Sir. Yeah, thank you so
And
much, sir.
it's almost magical the first time you see Markov chain Monte Carlo work.
Everything is like based on prior probability, and I was getting confused. In neural network, don't we use the same thing? Like everything is based on prior probability, the future probability based on the prior probability, and then you do back propagation.
No. You don't think there is no time here. So, okay, let me start the recording now.
Sir.
It's time now. So, Sukhpal, what you are saying is X goes in, then activate the first layer activation comes out. That leads to the second layer activation, all the way to the final layer activation. You think of it as time, but it is not time. This entire pass happens practically immediately because it's all matrix multiplication. In fact, the way the system treats it is as one giant matrix multiplication, right? W.
It is yes, sir. In Markov chain over there also we do probability matrix multiplication, right,
There
sir?
is actually a notion of time as step. So the other way to put it is that in Markov chain Monte Carlo, there is a sequential, there is a path. In other words, you say, you take randomness then. You start from somewhere and you take random steps.
Yes.
Whereas the neural network, in the traditional neural network, when you do gradient descent, there is no randomness. Once you have initialized the weight, in other words, you have taken a place in the parameter space, there is a very direct path with a little bit of zigzagging to the optimal point, right? This is your gradient descent path.
So this is the difference between neural network and this.
Exactly. There is no gradient descent in Markov chain Monte Carlo.
Okay.
It takes a completely different approach. In fact, it uses randomness. That is the interesting thing with the Bayesians. They somehow use the power of randomness to solve problems. Right? Okay, so that was a digression. Let me come back to what we are talking about.
Okay. Thank you so much.
Okay, welcome. No. So, where am I? Am I in this space? This page itself? No. Okay, here we are. So guys, where are we? We realize that the forward pass, input goes in and the activations keep moving forward, right? So X leads to the first layer activation, leads to the second layer activation, leads to the L-1 layer activation, all of it. Finally leads to the last layer activation, which is your Y hat. Right? The problem is this, in the beginning, all your weights in the beginning, all the weights are random. Oh, by the way, I must mention one more thing. Sometimes people ask, why can I not start a neural network and keep all the weights the same? So let me pose this question and think about it for a while. Saying at initialization. There are many ways to answer this, but this is very interesting. Think of a simple neural net, right? There is a, and let me simplify it down to just one input, X1. And it goes, and let's say it produces an output, Y hat, right? So this is your first layer. This one produces A1, and this produces the activation of the first layer 2, and this produces the activation of the 2, because there's only one node here. So what happens if all the weights are the same?
You basically have the same layer repeating or the same node repeating.
Right. So think about it this way. All the gradients, so if you have the same weights, if all the weights are the same, so whatever the loss here is, right? When you compute the loss with respect to this weight and this weight, it will be the same, right? If this weights were the same, the loss with respect to the any one of the second layer weights, but because the weights are the same, the gradient would be the same. So they would make the same step backwards. They will, in the second layer, let me just call it W, what should I call this? W21 and W22. So W21 and W22 will make the same step, right? 21 minus alpha 1, and this will be W22 minus alpha. You realize that if these are the same and the gradients remain the same, because there is a symmetrical situation, then even the modifications will be the same. So what you are looking at actually is a very interesting problem. You don't need so many nodes in the layer anymore. It is as though all of it is just one big node. Each layer is just one big node, because the other node is not learning anything new or anything different from the first layer. Do you see it, guys? Right? And even the forward journey is just adding, is just multiplying what one path would produce. You just multiply it by 2 because the other path is producing the same result and you're just adding it up. So people often they borrow a concept from theoretical particle physics. There is a concept called symmetry and symmetry breaking in particle physics. Or in physics, let's just say physics, because now it is condensed matter and all sorts of physics. In theoretical physics, there is a very powerful concept. It is called symmetry breaking. Which means that it turns out that in nature, for some reason, so imagine that you're sitting on top of a hill, right? A round hill. Just as an example, you're sitting here. This is a state of, this is not a, I mean, this is a very nice state. You are equally far from every point or whatever it is. But then if you slightly perturb it, shake it up, it will take a definite path down in some sense, right? So now, of all the directions, you have a preferred direction, or you have done something, or come down something. This is not a very good example, actually. We have a theoretical physicist amongst us, Chandra, who will probably give us a better analogy. But okay, the idea is they talk about some symmetry breaking. So something that was perfectly symmetrical is not symmetrical anymore. You have chosen.
As if you could do one thing in the same mountain peak, you can put a small, like a shallow. I mean, that is like a local minima there.
Right. Right.
At the mountain peak, you put a, then it's like a locally, it is like a very stable place.
That's
But
right.
you
Yeah.
put some randomness, then it's not stable anymore.
Then it comes out and you have a block. That's a great way of putting it. Yeah. So it is locally stable. You're right. And then, as Chanda pointed out, you take a preferred direction. Now you have made a choice, right? So that's that. So now in a network also a similar thing happens. So people are borrowed and they keep saying that in neural networks you need symmetry breaking. In other words, you cannot start with all the weights the same. If you do that, you're basically screwed because an entire layer will act as a single node. So you will end up with a lot of redundant nodes. Those nodes are not helping you at all. They're just adding to the computational cost. Guys, are we understanding this concept?
Yes, sir.
Yeah, it's a very simple concept. So in fact, there is a problem. It has some bearing on regularization. And now is the time to mention that. See, why is it that we do dropout? When L1, L2 regularization was there, and they work for almost every area of machine learning, they work. In neural networks also they work, but there is one problem. After a little while, some of these weights during learning, they begin to sort of resonate with each other. They begin to align with each other. They'll become multiples of each other or so forth, right, in the same layer. And so it is almost as though they have become the same. And there's a certain degree of symmetry that has come in. At least that partial subset of nodes then begins to act as one node. And so, you have lost some flexibility in the model. It's become a bit more brittle. You don't really have as many learning parameters as you thought you had. Do you see that, guys? Right. If that happens, and it's a little bit technical why it happens, but with L1, L2, one of the problems is this begins to happen. And so what happens is, imagine that there are two nodes. I don't know if you guys can see me. Let me see my own picture to see if you guys can see my hand. Are you guys able to see me? Yes. Okay. So imagine that you have two nodes and they both have essentially the same value. Right? One strong argument in favor of dropout is, suppose this node that I'm saying, in one step, one iteration, this goes away. This becomes dark. So now this node is there, it's alive, and this has gone dark. So I'll remove this. Now this is still there. So when the learning takes place, when the back propagation takes place, this would have learned and it would have moved away to a different value. It will not have the value that this node has, right? So in the beginning, if both of these have the same value, and I take this away, now after a little while, this has a different value. After this gradient descent step, this has a different value. And so they are not symmetric. Is this argument simple, guys?
Yes.
Right? That is the main, that's a very strong argument actually in favor of, so let me just put it in the diagram also. So it's in the notes and you can carry this. Suppose you have two nodes, node. And for some reason, the weights, one, W2, they begin to align themselves. So what happens is you notice that they're co-learning, right, in the backprop and so forth. Then there is a problem. So what you do is in step one, right, step one will be a forward step and backward step. Let us say that in step one, you go and nuke this. This is not there anymore. So this will have W2 will go to W2 minus whatever the loss W2 is. W1, and let's say that they are both equal to some value. let me take some value theta, right? And W1 is still theta. It doesn't change. Right? What have you done? You have broken the symmetry, isn't it? So that's an argument, a strong argument in favor of using dropout. A big argument in favor of using dropout. So, you know, these are the little things, guys. I don't know if your book, the textbook does mention it. I'm sure it does. This is written by one of the biggest guys in this field, the great pioneers. At some point it might mention. But, you know, it is these little things that makes this whole field theoretically very, very fascinating. I don't know if you're impressed, but I always find this very neat to think through what is going on as the neural network is learning. And it's very interesting, actually. We think when you read a book on neural networks, or at least hopefully I'll fool you into the understanding that you understand neural networks, these deep neural networks. But actually, I must say that that would just be fooling you because nobody really understands why these neural networks are so effective and why do they work so well in some situations, not in others. A lot of assumptions we used to make about them are proving not to be true. We know a little bit about why these neural networks work, but the underlying dynamics we are just beginning to study. And as we study it, you know, little gems keep popping up. There's an army of researchers, and they're all doing an incredible job of finding all sorts of things. Like all good research, it is a collective human effort to find things. But anyway, we will stop there. Now let's come back to the main topic at hand, which was backpropagation. What does this have to do with propagation? Right? So I showed you this example that the derivatives, you know, you can do chain rule to compute the derivatives way back. If something depends on something else, depends on something else, depends on something else, you can use a chain rule to get your work done. So now we'll apply it here. So let us say that this is a last layer. So I'll take a very simple neural net. Every layer has only one node. Are we together? So if it has only one node, then it will have W0 is equal to a bias term and W1, right? So if it has only one node, then the previous layer is putting out, and there's only one layer input. Input is one dimensional. Let's say that this is layer L, this is layer L minus 1. This is layer 1. Are we together? So what is the activation? What would be the activation of the layer L? This will be your y hat, isn't it? This is your output, guys. Do you agree? I'm creating a neural net, which is just a chain, simple chain of a one-dimensional chain. Each layer has just one node. Now, you know that given y hat and y, which is a reality, ground truth, you can compute the loss function, right? So the loss function could be MSE, it could be mean absolute error, it could be regression, Huber regression, and so on and so forth, regression, whatever your loss function is, I won't go into, or it could be a cross entropy, etc., for classification, right? So I'll just use it L, but just to illustrate, why don't we pin it down to regression, right? The argument remains the same whether we are doing regression or classification, but I will take the argument that we are looking at regression. So the loss function is given as y hat minus y loss. So sum over all the data points, right? And maybe you want to divide by n also, or plus regularization terms. Let's put it this way. So this is your loss function. Now that we learned regularization, you can assume that regularization terms are always there. So guys, tell me that this looks very simple. This is your sum squared error. By now, this must be as familiar as the, the back of your hand. Are we together, guys? Please give me some feedback.
Yes, sir.
Yes, right. So now we'll ask this interesting question. This is a weight W at the layer WL. Let me just say WL and WL1, right? So let me just use let me use a simpler notation. Okay. So now tell me, how do I update this weight? For me to update this weight, I need to know. So suppose you make a small change in the weight W, right? How much change? Let's look at what happens. If you make a small change in weight, in the last layer, W, and by W I mean the weight, the slope here, let us say, right? You can put 1, 0, whatever you want, or a small change in the bias of the last layer. This will trigger, what will it do? It will trigger a change in Z, because Z is B plus W of the last layer times the activation of L minus 1. So a small change in weight will trigger a change in W, guys. Is that simple? Guys, is it making sense?
Yes.
It's just, this is just your direct multiplication. Now a change of W, Z, will cause a change of the activation, whatever activation function there is, right? Because what is it? The AL is nothing but the some activation function on ZL. So this will change the activation, namely the output, right? And that change of output, because see, now look at this. What is Y hat? Y hat now in our notation, I could write it as activation of the last layer. Now this formula, I can write it as 1 over N I of all the data points of activation of the last layer produced by the ith data minus yi square. Would you agree with that? So therefore, what will this do? It will cause a change of the loss function. So the thing is, you perturb this, you make a minor perturbation of the weight, a small change of the weight of the bias, and it will have a cascading effect. It will change W, which will change activation, which will change the loss. So far, so good, guys. So this is a chain reaction for you, right? In a line, one causes another. Now, if you get this, now look at this. Now you ask yourself, how much is the effect? So you say that a small change of activation, like suppose you have a small change of activation, right? How do I relate all of this? Let's start with this, B. Let me just take W, right? W of the Lth layer. Let us compute how it works. So the way to think about it is that, look at this chain reaction. You say a small change, how much L will change if you change W a little bit? So the way to pose this question is, how much sensitivity does loss L have to a small change in WL, right? So you make a small change, and how much did it change? If it changes a lot, then the ratio would be huge. If it changes only a little bit, then maybe the ratio is small, and it probably means that this little W does not need to be changed. It is not having much of a material effect in decreasing your loss or changing your loss. But let's work it out. This change of W is causing a change in ZL, which is causing, now, but a small change in ZL. Now, how sensitive is the activation function to a change in ZL, and how sensitive is therefore finally the loss with respect to AL? So little change you can't compute it directly, but you can ask it step by step. Suppose I make a small change, it will lead to a change in Z. So Z will be sensitive to W, and changes in Z will A will respond to the changes of that, and then changes in A, L will respond to it. Right? So the staggered effect is if you could compute these sensitivities, you pretty much know how much the loss is sensitive with respect to this weight. Am I making sense, guys? Yeah. So this is essentially your chain rule, isn't it? Now let's see, can we actually compute it? It's very, very simple. So let's take a particular case. In particular, we'll take a Euler if, and this is the big if, I'm just taking a particular case. L is equal to 1 over n AL minus y square. And, there is a I here and the summation over I and so forth, plus rectums. So I'm going to, skip some of the notational aspect, right? So now let's look at this. Can I find, like, by the way, these things in the limit of very small, in the limit of delta W going to 0, these things become derivatives. So you say, so this is infinitesimally small. So imagine infinitesimally small change in W. This is equal to ZW. So when people write this partial derivative, all they are saying is that it has to be genuinely very, very small. This is it, right? So now ask this question, can you compute this term? This term. Of course you can compute. Look at your loss function. You can say DL, DAL is equal to nothing but 2 times 2 over n times summation over AL I minus YI. Right? This is just calculus. The derivative of square of x is 2x, isn't it? ddx of x squared 2x. What is x here? X here is this term AI minus y. So guys, do we like this result? It is a known. Now we ask this question. So can somebody speak up? I need some feedback. So far so good, guys. Is it easy to understand? Anyone, please?
Repeat that, the delta L by delta AL, and then you're drawing this arrow. How did you come to that conclusion?
Which conclusion? This one here?
Yeah, last week.
It follows from the fact that L is equal to summation over I, 1 over n, AL minus y square. So now ask yourself, what is the derivative? So I'll just forget the I subscript. What is the derivative of L with respect to the activation? You can take any one particular activation. This is averaged over all of them. So what do you think this is? It is a function of A, right? It's a square term. This would be 1 over n and summation over I and all that. Now what is this? What is the derivative of this term? 2 times AL minus y. I'm forgetting, I'm skipping the underhand subscript. Do you see this, guys?
Yeah.
Does this make sense?
Yeah.
Okay. So that is where I say that this is computed. This is easy. And now we ask the other question. What about the second term? Let me use a different color here. What about this guy? Right? So for this guy, also it turns out that it's not that hard actually. It depends upon which activation function you use. So suppose you use an activation function is logistic, right? So logistic A of Z is equal to 1 plus e to the minus z, right? This is the largest step. Then it could be is tan h. Az is equal to e to the z minus e to the minus z, e to the z plus e to the minus z. And I might have interchanged this term, so I keep always messing it up. So beware, right? Take it with caution. So these are examples of the activation functions. Examples. Function. If you take ReLU, which looks like this, ReLU, and we'll cover activation function in detail. It is even easier. So suppose ReLU, you take a slight bend here. So either the value is AZ, this is AZ is defined as either 1 or 0 based on whether Z is greater than 0, Z is less than 0. So again, you can take the derivative at any given value of Z except this one singularity. Right. So now it's a very interesting thought. Can I find what we are looking for is A Z with respect to Z, right? Or of a given layer. So suppose I put a layer here. Layers doesn't matter. So can we do that? So you can confirm that a very interesting fact, those of you who did engineering mathematics with me would remember, for sigmoid, this is a function we can of course take its derivative, and you will realize that, and I'll use prime for derivative. Symbol A prime, which is the same as dA dz, is equal to, believe it or not, A, it is equal to 1 minus A. Surprising, isn't it? It comes out to be very elegant. For tan h, in fact, this was one of the assignments if you did engineering math. A prime happens to be 1 minus A, 1 plus A. In other words, 1 minus A square. So if I have the activation, do I have the value of A? Of course, I have the value of A in the forward pass. Do you remember that in the forward pass, what happened? At each step, I know the value of A. I keep computing the value of A. So I know A, and therefore I know its derivative, because the derivative can be written in terms of A itself. Are we together, guys? Right? So the blue part is also taken care of. Then comes the last part, which I will take another color to do. What about this part? Well, it turns out that this is the easiest part because Z of L of a given area, let me use a different color here. Yeah, Z of L is, if you remember, what is it? It is the bias of L, the bias term or W naught term, or the bias term of the L, plus what? The activation of the previous layer times the weight in this layer. Do you remember this expression, guys? Guys, are we together? Just this, right? This is a simple multiplication that we did. A linear, just the linear product plus a translation. That's how we define Z. This is practically the definition of Z. So then I can say dz, d, what do I want to compute? A dw, right? dw of L is equal to what? It is just the activation of the previous layer. And we have a result here. Now, when you put all of these results together, what do you find? You find that you have computed dl, dwl is equal to, well, dzl, l, dwl times the activation of L times the ZL times the loss function DAL. Remember, this was the original expression, and you just computed each of these terms. So you for example, found that this is equal to AL minus 1 times AL AZ. If you take sigmoid, it is AL 1 minus AL. I'm just taking the sigmoid for logistic. 1 minus AL times, and now what was that? This was 2 times whatever it was, 2 over n summation over I A L minus yi. You see? And so what has happened, guys? I have managed to compute exactly what this is. So far, so good, guys? Guys, I hope what I'm saying is just multiplying the derivatives, the chain rule, right? Can somebody please give me a feedback if you understood this? Premjit, is this clear?
I'm following Asif, but I would need to review it once more to kind of put all things together in my head.
Okay. Yeah, so it is, what we are saying is that, you compute a lot of things in the forward pass, but if you know your mathematics, then the backward pass, you can use the chain rule and those pieces that you computed in the forward pass to plug it in. Say everything comes from the forward pass, right? You can plug that in to compute the derivative. And now observe something very interesting. This function, this guy, depends on, ultimately after, these parts are easy, but it depends on knowing the derivative of the loss function with AL minus 1, isn't it? And so you can argue that you can generalize from that, and you can say of L minus 2, L minus 1 would be something in the previous layer would be DZ, right? L minus 1, which is again dW L minus 1, dA L minus 1, dZ L minus 1. The same thing applies. There's nothing special with L, except that you need to know dL, dA L minus 1. So the question is, in the last layer, it was easy. We could use this formula for the loss. But what about any layer before that? Here, we need to find this out. So it turns out that also we have a chain rule that you can do, and you can argue as follows. You can say that, suppose I know this for the last layer, dL dA L minus 1 is equal to, so small change in A L minus 1, A L minus 1 will cause what? It will change a small change in Z of the Lth layer, and the rest of it remains the same. Change in the Z of the Lth layer will cause a change in the activation of the Lth layer, and DL, deactivation of the Lth layer. And so we have a relationship. We can find these activations, the sensitivity of loss to activations of any given layer, by knowing the sensitivity of loss to activation of the layer ahead of it, right? And that is why you say that the direction of computation is backwards. You first compute the Lth layer sensitivities to find the sensitivities in the L minus 1 layer. And again, these are known, if you realize, this is nothing but the weight in the Lth layer. This again is AL, 1 minus AL, if you are using logistic, and this is whatever you computed so far, right? And that thing, this thing, the fact that you can layer by layer compute it, is called back propagation. Are we together? This is the back propagation algorithm. So guys, I will post these notes, and obviously the video will get posted. I want you to understand at this moment, see, if you have followed it through, then you can watch the video a couple of times and grasp it. Now, what happens here is that once you get it, you realize that it's trivial. But till you get it, it all looks confusing because there are all of these layer coefficients and ijk and all of that are flying around. Right? So let me just review it, and then I would like to take some time for the lab. What we are saying from the beginning is that, first of all, let me go back. We go back and learn about the chain rule. There is a chain rule in calculus. Basically, it helps us decompose a complex problem and solve it piece by piece. When something depends on something, depends on something, depends on something else, depends on something else, it's a huge chain of relationship. You can deal with that sort of a complex chain of relationships like this. X causes, X causes Y to change, Y causes W to change, W causes Z to change. So when you have this causal chains, then a relationship chains, then you can apply the chain rule to deal with that problem. Now we come to the review that a node is nothing but weights producing weights inputs, weights producing Z, and then the activation of Z. Remember the analogy, the magic box that I told you. Z, these are the weights, these are the inputs. What just happened? Okay, these are the inputs, and this is the distortion function, A of Z. Okay? And this produces Z, and this is it. So once we have this idea in mind, then we look at our neural network and we realize, oh goodness, any one Z, any one weight, it has certain coordinates. It belongs to a certain layer, it belongs to a certain node in the layer, and it is the weight associated with some input component, right, coming from the previous layer. So you need 3 indices to uniquely identify a weight in a neural network. So what it means is that this is our parameter, and we need to find some way to do gradient descent with respect to this weight. We need to be able to use a bit of magic here, a chain rule magic, to be able to compute that. So we do it in 2 passes. In the forward pass, to see, ultimately what we need to do is we need to do this gradient descent step with respect to any arbitrary weight. But to do that, we need 2 passes. In the forward pass, we just compute all the inputs and the activations and all the way to the output. Then we compute the loss. Then from the loss, we start computing the gradient layer by layer from the end to the front, right? So we start moving back layer by layer and computing the gradients, or computing this, right? And the main idea is that these are, at the end of it, when all the dust settles, it just comes down to one simple thing. Any change sensitivity of loss to a given weight, which is what you need. This is your gradient that will help you do gradient descent. It depends upon, in that layer, depends upon the sensitivity of loss to that layer's activation. But that layer's activation, you can relate it to the sensitivity here, gradient here, related to a gradient of the layer ahead of it. So you can keep computing backwards. So likewise, you can imagine that, see what, the way it would work is, suppose you have the last layer, loss AL will come out, and you can therefore compute. So let me go step by step. You can compute this. This will help you compute DLW, the last layer weights, and then this will help you compute DL, the activation L minus 1. And actually, let me write it in as a vector, as a matrix, as a sort of a notation like this, just to simplify, otherwise we'll occupy a lot of space. So if we know this, then all it is you need to know what your activation function is in a basic amount, what their derivatives are. This will tell you, and now you can DL, DWL minus 1, and then that will help you tell DL, DAL minus 2, DL, DWL minus 2, and it keeps going up till you find the derivative ultimately of L, the A1, and a DL, the weight 1 of the first layer. Right? And ultimately, you reach here. You keep back propagating. And this is your back propagation. And once you have back propagated, you can therefore take the step, because after this back propagation and all the gradients being computed, all you have to do is change in W next of any one layer, and I'll just skip the layer and notation and so on and so forth, right? Is the W value minus the DL DW, right? And here I've erased all the, implicitly there are all these indices, layer and I and J. And so this is the step, learning step. So the way it works, and if you remember in the code we did that, this was there in your quiz. What would you do? You take a network, if you remember your code, you take a network, you give it the input, it produces the prediction, the output, right? Output. So this is your, then you say loss is equal to a label loss function. If you remember, loss function in which you gave the labels output. Outputs. Right? And once the next step is, so then let me go. And then what do? You do backwards, right? Network dot backward. What is this doing? Back propagation, back prop of gradients. It computes all the gradients. Cleverly computes all the gradients. And once you compute all the gradients, then all you have to do is you have to take a step. Right? You take a step. What does the step do? Step does the gradient descent. Because now you know the gradient, so you can do the gradient descent step. So the word step refers to the gradient descent step. This is what it is referring to. Are we together? And so if you go back and read the code, you literally see the logical structure. So what are the forward passes? Which of these are the forward passes? This is the forward pass. Which of these are the backward passes? Backward passes. So the learning takes place in the backward pass. And once you have trained a neural network, of course, you don't do the backward pass. You only do the forward pass, and you freeze the gradients. Right? You freeze the parameters and you freeze the gradients. You don't let the gradients be updated anymore, or the weights to be updated anymore. Am I making sense, guys? So that is how neural networks learn. It's very simple. Right? Layer by layer, they learn. Now, if we are done, I would like to take another 20 minutes to get back to some amount of lab just for fun, because I'll release it. We are a little bit behind at this moment. We are half a session to one session behind. So in the end, I'll add a session if needed, or we'll do it in the extra sessions on Saturdays or something. But I would like to show you a little bit of a lab that I'm going to upload.
That's it.
And I won't take too much time. I know that we are running out of time now.
Yeah, that's it. Can you hear me?
Yeah, go ahead.
Yeah, I have another meeting at 10. So would you keep this the YouTube till you post the recording?
It is automatic. See, guys, let me remind you that when a lecture finishes here, it is already there on YouTube. There are a lot of people who at this moment are watching it on YouTube from our for our participants, right? Some of them are here, but they are simultaneously watching it on YouTube on their big TV. And
yeah,
it will stay there, but not for long, because ultimately, you guys are paid for this workshop. It cannot be a public video. And so what happens is in another 8-10 hours, the official video, 12 hours, the official video will come out. and then the live streaming becomes private. I take it down. And
Okay.
if you go to the course web page, you always find all the recordings. And let me remind you of that by going to the course web page now.
So the YouTube recording or the session there will be available till the point you post the recording on your webpage.
Yeah, it is available usually. I don't keep it too far available because I notice that then suddenly other, like you can clearly tell that there are people who are not registered who are all there. And that becomes unfair to people who are registered and have paid. So I take it down pretty soon. The only reason I keep it there for a little bit is because some of you, you join the class late. So you can actually start the video from the beginning and catch up to it.
That's exactly the point. So it gives us time to catch up if I miss.
You notice that this live now,
Yeah.
the session, so it is actually live now. Here. So you see it down pretty soon. Literally this, I'm showing it to you guys. So it is live. And then if you go to the course web page, which we should do now, let me do that. Let me not, I'm still reading this article. I'll keep it quick, guys. This explanation will be very, very short. Supportvectors.io. If you go now to this page, where are we? Just a reminder, guys, that you can just go here and what was the lecture on Monday? Regularization, isn't it, guys?
Yeah.
And here it is. If you click on it, it will take you straight to the YouTube. So all the lectures keep showing up either in the live section or in this place. Are we clear, guys? Simple. So now let me show something to you in this notebook. What I did is, I want to take a simple example as a base. And now we want to understand classification and regression from a metric perspective. Till now we have done code. We know that neural networks can be trained to do regression and classification. Both are prediction mechanisms. The question that arises is, how good are the predictions? And how do you know those predictions are good? So the next lab we will give to model metrics. What are the metrics? How do you know that something is good or bad? Right? So for that, those of you who have done workshops with me in the past, you will be familiar perhaps with this particular notebook and this river data set. It's a very simple data set. I'll just walk you through it, through this a little bit. This data set looks like this. Right? So there's yellow points and there's this purple points. And you have to write a classifier that can distinguish between the yellow and the purple point. In this particular one, just to illustrate, we have used the logistic regression. This is literally how we did it in ML100 and 200, actually ML200, and we just show how you should do careful feature engineering and so on and so forth. And you can solve the problem, you can look at it, but what I want you guys to focus on is the model metrics. Just read it, see if you can understand it. Next time I'll explain to you, both in classification and in regression, what are model metrics. We will take the river here and maybe the breast cancer data, and we'll take the California housing data. The purpose is just to illustrate the concept of the goodness of fit, or the goodness of a model. How do you quantify it? So read it. Now what I have done is at the end of this river notebook, I have also put a toy example for you. I have taken, and again, the code is there. There's a binary data classifier. And by the way, I've deliberately kept the code a little bit imperfect. Yeah. So see if you can improve upon that. What it does is, I'll walk through it. This is just importing all the classes. There is a binary data network. You can choose how many hidden layers you have. Then you create a classifier, then you load the data. Now you notice that we are training the data. This is something not something we didn't do with CFAR. CFAR dataset, you remember, it was already pre-trained. We downloaded and we used it to make prediction. But here we first train it and then we make predictions. Very much like you did with the universal approximator. So here you go. This is the loss taking place. And then here is the classification report. Well, this report is too good to be true. It is. The neural network does an amazing job of classifying it. It is comes up with a perfect score, right? No mistakes. The data had no noise. I didn't get time to introduce noise, but this is it. So this is it. Now, if you plot the prediction versus the reality, this is what the reality was, and this is the prediction. If you look at the prediction, do you notice that there's no sharp edge here? It's a curve, it's a round curve. Do you see that, guys? At the bottom, I don't know if you can make out, it's a good, nice round curve. It's not very sharp. And now there's a bit of homework. Do this. At this moment, you can do this without even getting too much into the model metrics. Go read the code and see what happens if you change the activation function from ReLU to tanh. Then play around with the number of epochs. What happens if you run it for less epochs? Then change the number of hidden layers. Oh, no, this should be hidden layers, sorry. Number of hidden nodes in the number of nodes in the hidden layer to see what is the minimum number of nodes you need. And obviously, it is something I talked about. Remember when I argued for neural networks being universal approximators, I made that argument. So you just see how many lines there are and how many straightenings you have to do. If you attended Ola's, the Saturday session, Sunday session, it should be even easier. This thing is two-dimensional. How do you unfold this manifold in such a way that it becomes a straight separator? So go, you can do it. If you reason like that, you'll be able to answer these questions. Lastly, I've left you with a problem, genuine coding problem. You have the river data set. Can you classify the river data set by using this code? So the hint is, if you just directly feed in this code, you may not succeed. You'll have to do some small changes to the code. And this should give you time to play around, fool around with the code and make modifications to it, and so on and so forth. So see if you can do that homework. Huh? I'll leave you guys with that much. Any questions, guys?
Asif,
Yeah, go ahead.
When you apply max drops, does that apply during the feed forward step or only during backpropagation?
Sorry, when we apply what?
Max drops.
What is max drops? Oh, you mean dropout?
Oh, dropout, sorry, dropouts, yeah.
Good question. You only do it in training because, what are you doing? So suppose you have two nodes. You take this away for one batch, then you take this away for another batch. At the end of it, when it is fully trained, you keep it both, but suppose your dropout ratio was 30%. So now what happens is, if you keep all the nodes, initially, let's say that the layer had 10 nodes. So only 7 of them were being activated. 3 of them randomly were being passivated. Then your total Z came from 7 nodes. And now it is coming from all 10 nodes. So what you have to do is, you have to scale the Z down. You have to multiply the Z by 0.7. Otherwise, it will get amplified. So you bring back all the nodes, but during evaluation, you just amplify it a little bit. And the good thing is networks take care of that for you. Good thing with PyTorch is a lot of these things essentially are taken care of. Are we together?
Okay.
If you go into eval mode, it will smarten up and it will take care of it. All right, guys. Any other questions?
Have you uploaded this homework?
Yes, I'm going to upload it right now, guys, in a little bit. So by the time you guys wake up in the morning, you'll see I'll upload it in the next few minutes.
Also, the week 3 video upload is just 1 hour 15 minutes.
What you say? Hang on. I don't believe so. Let's go and see. You're saying that the video on
Week 3.
Okay, let's go to the class and see what we are talking about. This week 3 video, regularization in deep learning, is only 1 hour 16 minutes. Oh, so it is possible that the videographer has taken it before the break and not put the stuff that came after the break.
Yeah.
So then it means that another video is coming. I'll put part 1, part 2 there. That's a good observation. Let's wait for the next video and we'll put it there. Any other questions, guys? Go ahead, Prachi.
Harini here.
Oh, Harini, go ahead.
As if in Colab 3.8 Python is not, I'm not able to install and work on it. So how do we go about doing it? I needed help.
Did you try pip install Python?
Yeah, we tried. It says the version is not there or something. There's an error.
Asif, I read about it online and they say that Google doesn't support yet for Colab the version for Python.
Okay, guys, so what I'll do is I'll backport the code. I'll remove that part which uses a Python 3.8 functionality. I'll put patch it so that it works with 3.7. Then you can run it.
Internet program works, and after that, none of it is working.
I didn't hear it. Your voice is fading.
So the first week, only ImageNet worked. After that, none of the notebooks work. There's some error or the other because of this.
Guys, are all of you facing this? Anil, are you also facing this?
Haripriya is also having issues with
Colab once, Asif. Otherwise, everyone has to upload 3.8. So I'm doing it on my local environment, and I can.
We sort of verified in Anil's environment that everything is working.
It's all working as if Colab I didn't check.
I'm sorry, say that louder, please.
Locally, everything is working as if Colab I need to check.
Check it out. No, because the reason is with Anil Pandey, he was the first who wanted help. So I helped him and then I made everything work in Colab. Maybe I need to go see what steps we did to make it work for him in his Colab. I'll post those steps. Otherwise, I'll backport the code. There's only one line, the unlink, one line that needs 3.8. So I'll replace it with something that is older version compatible. All right.
Asif, can you keep both the versions if it's possible for the code?
Of course. I'll comment it out and I'll put a comment there saying with 3.8 use the new version. See, the difference is this, guys. People used to deal with files, directories, using the OS and system, the packages. But just as in every language, like with Java, you have the lovely NIO packages. In Python also, they have modernized the IO, right? The file system access and so forth. So there is a pathlib package. And the preferred way or the recommended way now is to use the pathlib. They're still building it out. So every version, they add more features to it. I just happen to use the features that I had on my machine, which is updated to the latest. And so I need to backport it. Remove that and just use the older API. It is just for the file delete, one thing, one line. I'll just change that.
Thank you, sir.
Asif?
Okay, go ahead.
So for every step, you update all the weights from all the layers, right?
Yeah, the backward step updates all the weights in all the layers. layer after layer after layer backwards. That's why you call it the backwards. It's like a back, it's like a wave that's propagating back.
Do you have to like go back to change like the later layers after you change the earlier layers?
No, it doesn't work like this. So okay, let me once again show what we mean, and I'll have to share my writing screen for a moment. Are you seeing my writing screen?
Yeah.
So suppose you have layer 1, layer 2. Let's just take layer 3. And this is the activation of the layer 3. So X goes in, activation of layer 1 comes out. That produces activation of layer 2. That produces activation of layer 3. And that produces the loss. Right? So from the loss, what do? First, you compute D. So this gets computed first, loss, with respect to, here, I'll just put two things, A3, W3. I'm just writing it in a symbolic manner. It means the gradient with respect to both the activation and the weight. This will get computed. So this will be first, number 1. Now, once this is done, then you go back to number 2. You move back to number 2. And here now you can compute, using what you computed here, using this you can compute now A2, W2. You need this. This is number 2. You can't do number 2 without doing number 1.
Right.
Yeah. And then then you move back again, one more layer, and then you can compute WL with respect to A1, W1, and then you're done. That's it. The moment you have all of these 3 things, what does it mean? Gradients are done. And so the network.step will do what? The network.step will just invoke the gradient update, because all the gradients are now found. And so gradient update you can do globally at one go. Like you don't have to do one at a time. It is just a standard matrix multiplication.
I see.
All you needed was the gradients.
How do you exactly update that? Like, I just want to know like how the math works.
How the math works? It's literally matrix multiplication. Like we said, let's go back and up and look. We computed, like in very practical terms, if you remember, let's look at this example, right? The sum squared error. And let us take the example of a logistic, a sigmoid function. So we happen to know what is the derivative of this with respect to A. We already know it, isn't it? Like the guy who wrote the sum squared loss, the guy who wrote the class called MSE loss, guess what he did? He wrote this, he baked this formula into the code.
Right.
So it is baked in. It's not that the computer magically finds the derivatives, but the creator of that loss function had to bake in this formula. Then what happens is then what is the derivative of this? This you remember is the activation function. So for every activation function when you create, you are required to also tell what is its derivative, right?
Right.
You bake it in. So all you're doing here is plugging it in. At the end of the day, if you look at this is computed. This is just this activation loss, and of course the activation.
Yeah.
So therefore, it is just simple multiplication. Once the gradients are found, it's just simple multiplication.
Okay.
That's all it is. So guys, we learned about backpropagation. I'll put up this code. I'll also put up the California dataset. Do you guys remember the California dataset? Some of you from the ML100, 200. So that will make 2 good starter points. So let me just say river, a dataset, the California housing price prediction. Now that, of course, is a favorite pastime of people here in Silicon Valley. I'm told that people almost every few months they go and look at Zillow or whatever it is, Trulia, to see if their house value has gone up or down. So, well, we are going to use that data set and we'll try to predict the house price. One reason to do that is these are very good data sets to learn from. Also, we have done extensive notebooks on it if you have taken the previous class. So then it puts the neural networks in perspective. How do you use the neural networks? And your homework this time is for the toy data, which is V-shaped data, you can see what does the change of epochs, size of the hidden layer, and the activation function. Those are all your hyperparameters, right, in a sense. How do they affect the efficacy of your model? And read the river data set to see how in machine learning we quantify the metrics, the goodness of fit of a model, or the quality of performance of a model. So read it and you'll get some insight into that. All right, guys. So I'll stop the recording. You guys, if you have questions, you can.
Asif, just one. Yeah, you can stop the recording. This is just a different question. Just one observation.
Go ahead, sir.
Yes. So just the observation. One small observation. The ML200 videos are still public on the YouTube support vectors page.
I'll take them down.
Yeah, if you can.
Definitely, I need to take them down. See, as I said, we are going back and fixing the situation. We have a new videographer, so it's still in the process of training him.
Yeah. It was just an observation. It's.
So guys, was this session useful, or you guys are very quiet today? Did we understand this? This is about as complicated as it will get in neural networks. This is it. There are no more mysteries, theoretically.
We followed, I followed it properly. Maybe like a refresher, look back at the video again and it'll make sense, complete sense.
And if you notice in the class web page, I have put couple of videos on backpropagation by these people, 3 blue, 1 brown. They are a group. I think they must be very funded because a lot of people, if you look at the list of contributors, it's a large list of contributors. They make excellent videos explaining concepts. So I've pointed to those videos. Do watch those videos. It will be the best review. And after watching the review, the videos, then go back and read the textbook, the deep learning textbook, and you'll see the discussion of deep learning there. And we can review that. So do review, guys. And today, this week was theory heavy, but this is the core of deep learning. This is it. If you understand this, you understood both the deep and the learning part in some sense. Deep is the layers and the learning is the backdrop. Right? Gradient descent and backdrop. That is it in deep neural networks. So do please review this. This week is very important what we learned. Review the videos. I'll make sure that the second part of the video also gets posted as soon as possible. And let's take it from there. Any other questions, guys? Otherwise, I'll end today's session. All right, guys. So I wish you all a good night. And those of you who are dialing in from India, I wish you all a good and productive day.
Thank you also. Good night.
Bye.